Thank you very much. This is the joint work with Shannon Liu, who is from Huazhong University of Science and Technology. Very quickly, overview of the talk. So in this talk, we're going to establish information-theoretic extensions of the celebrated Shannon-Nyquist sampling theorem. And our extension will take the form of sampling theorem or approximation theorem, which you will see in a moment. Okay. So the idea is pretty simple. So let's say we have a continuous time Gaussian channel. Then we sample the Gaussian channel so that we can have the discrete time Gaussian channel. Then the sampling theorem actually says that the mutual information of the obtained discrete time Gaussian channel will converge to that the original Gaussian continuous time Gaussian channel as the sampling gets finer. Right? The idea is actually pretty simple. But this is type of result that is easy for everyone except for the author, maybe. So the result sounds intuitively correct, but if you really want to get a precise statement, if you really want to have rigorous proof, you need to add on some details. So, but the bottom line still, idea is pretty straightforward. Okay, so you need to relax, sit back, and take a nap if you want to. Then our extension actually gave us the ideas and tools to recover some old results in information theory from a new perspective, and we can also obtain some new results. So in particular, we are able to derive the capacity regions for families with continuous time one-half Gaussian channels, and we are able to use this extension to analyze how feedback affects the capacity regions. Okay. So very quickly over the overview. Okay, so the continuous time Gaussian channel have been examined by Shannon ever since the beginning of information theory using the so-called bandwidth approach. And the backbone of that approach is of course, the celebrated Shannon-Nyquist sampling theorem. And here's the theorem. So let's say we have continuous time signal ft. Let's assume this signal has bandwidth limit w. Then we sample the continuous time signal every 1/2w seconds. Then we have a lot of actually infinite many time samples, right? So the theorem actually says that the original continuous time signal can be exactly recovered by all those time samples. And here's how you can do that. Right? So this is a very famous sampling theorem. Okay, so as I said, this theorem is the backbone of bandwidth approach. Okay, so let's see how the bandwidth approach works. Of course, it can be more general, but let's just look at it in additive white Gaussian channel for the moment, just for illustrative purposes. So here, the additive white Gaussian channel formulated by using the white noise. As usual, X is the input, Y is the output, ZT is the white Gaussian noise with a flat power spectral density. We actually assume the average power constraints on the channel input. Right? It's a typical channel. Probably in Communication 101, you already seen that. Okay, so then I'm not assuming any bandwidth limit for this channel. So, but right now to analyze the bandwidth limit, the capacity. So we want to assume the bandwidth limit W, apply the Shannon-Nyquist sampling theorem. So we have this channel. A very subtle point is that the index over n over here actually is not time index; it's a space index. The idea is that Zn is the coefficient you obtained after you decomposing the white Gaussian noise with respect to a orthonormal basis. So Zn is really some coefficient. But when there's no feedback or memory in this channel, you can actually view the space index as time index. So that we have a discrete time Gaussian channel, right? But for such a channel, we know how to do. We have a lot of experience working on this set of channel. We have a lot of tools to analyze them. So if assuming the bandwidth limit and apply whatever we know about discrete time Gaussian channel, then we can compute the channel capacity with bandwidth limit W. So this is the renowned formula by Shannon. Right? So this formula, I'm sure you've seen it many years ago. Then remember our previous channel actually doesn't have bandwidth limit. So then taking the W to infinity, so then we have the channel capacity without bandwidth limit, which is this formula. This also a very important formula C equal to P over here. Right? Okay. So that's how bandwidth limit approach works. Basically, we assume bandwidth limit, then we convert it to discrete time channels, and analyze it, then we take the limit. Okay, but there are some issues with the bandwidth approach. The number one issue, so any signal cannot be bandwidth limited or time limited simultaneously. Well, it's the basic property of Fourier transform. So which means you can't really define the data transmission rate if you assume a channel has bandwidth limit in the first place, because the signal already doesn't have any time limit, right? So you can't really define data transmission rate. This issue is widely known ever since the bandwidth approach was proposed, but it can be overcome by considering those signals with almost bandwidth limited and almost time limited. And in particular, Slepin actually in 1970s introduced this so-called prolate spheroid wave functions for such a purpose. Okay, the second issue, actually, the argument I just gave you only gave you a lower bound for the capacity for for P over 2, because basically tell you how to achieve this P over 2, but it doesn't say any other coding scheme cannot go beyond P over 2. And this issue has been noted, by the different authors, particularly in Ash Information Theory book. It's a very old book in 1960s. You actually can find a rigorous proof about why P over 2 is the capacity for the continuous time channel. Okay, so the third issue, which is more related to our to this work, is that this approach actually difficult to handle or even incorporate continuous time feedback or memory to the channel. As I said before, when you do the conversion from continuous time to discrete time, the Zn, the n over there, actually is the index of space, not time. So when there is a feedback or memory in the channel, so after the conversion, so the discrete time channel you're looking at actually already destroyed the temporal causality that the original channel had. So it's very hard to deal with the continuous time feedback or memory for such approach. Okay, so we're going to do in this talk, so we're going to extend the Shannon-Nyquist sampling theorem to a case that will accommodate feedback and memory, and we're going to propose our approach to deal with continuous time Gaussian channel. Okay, so here's our approach. So the starting point of our approach is the so-called Brownian motion formulation of AWGN, and so basically it's the integral version of the the white Gaussian noise formulation of the AWGN, because as you may have already known, so in a sense the integral of white Gaussian noise is Brownian motion, right? So this is the integral version of the white Gaussian noise formulation of the AWGN. So here Bt is a standard Brownian motion. Right now you're looking at the integral. So Yt is not exactly the same as the previous Yt, because the integral of previous It. Okay, so then we're going to sample and approximate the about AWGN to obtain the associated discrete time in Gaussian channels. So now before we have continuous time channel, right now after sampling we have discrete time Gaussian channel. Then our sampling or approximation theorem, which I'll show you later, so we will guarantee that the discrete time Gaussian channels can be arbitrarily close to the continuous time channels. So instead of studying the continuous time Gaussian channel, so we can study this discrete time Gaussian channel, then we take a limit, right? So it's somewhat similar to the previous approach. Okay, so the advantage of our approach is as follows. So the first thing aspects should be attributed to the Brownian motion. The Brownian motion has its pathwise continuity. So Brownian motion does allow sampling approximation with respect to time. And you cannot do that with white Gaussian noise, right? So any time samples of white Gaussian noise doesn't give you any information about white Gaussian noise. Even the infinitesimally small neighborhood, it doesn't say anything about that. So and also the second issue I showed you, if time permits. So the Brownian motion formulation supports many fundamental notions in discrete time. For instance, mutual information capacity, or random coding arguments you have seen so many times in discrete time. Okay. And also, this is actually more or less related to the third issue of the bandwidth approach. So the sampled will approximate the channel consistently inherit temporal causality. So before the bandwidth approach actually destroy the temporal causality. And so now, so we have a natural connection between the continuous time Gaussian channel and discrete time Gaussian channel, even if we have feedback or memory. Yes?
So as you say now, because you have a continuous path process, the Brownian motion, you get sampling time, but you don't have white noise.
We do have white noise. I mean,
the derivative is white noise, but if you sample...
Oh, you're right. But so, okay, very good question. I mean, so you can actually, right. I mean, you can actually prove that the Brownian motion formulation of AWGN is equivalent to the white Gaussian noise formulation of AWGN if you do the orthonormal basis decomposition. They actually have the same mutual information. So in this sense, they're equivalent. But you're right. Brownian motion is not white.
But where do you sample? If you sample in time, like you've written it, it's not white noise anymore. You have to look at the derivatives.
Yeah, I will show you, but basically you're right. But right now the BT is not white at all. So it's very much colored. So when we sample, so let me show you the sampling. Let me show you the sampling. So the sampling actually is very much innocent. So before stating the sampling series, let me just describe the setup and introduce more notations and tell you how we sample the channel. Let's say we have this continuous time white Gaussian channel. Here I'm mentioning white Gaussian channel. I don't mean the BT is white. I mean it's the integral of white Gaussian noise, but it's equivalent to the original channel in information-theoretic sense. So here M is the message to be transmitted through the channel, and we actually have a feedback. Right now it's a continuous feedback. So Y from 0 to S minus infinite small neighborhood of S. So right now you're looking at a Gaussian channel with feedback. Let me do sample. Here's how we do the sample. It's basically just for a prescribed time points, for instance T0, T1, Tn, then we just take a snapshot of this channel. For instance, we just evaluate this BT and this integral and the output at Ti, and this is what I meant by sample. Right? So I'm not sampling the white noise. It doesn't make sense to sample white noise. So that's the more notation I want to introduce. So now we're ready. As I said, the idea is pretty simple. So now we're ready to state the sampling theorems. So roughly speaking, as I said before, as the sampling gets finer, the mutual information for sampled channel converge to that of the original continuous time channel. So put it more rigorously. So assume some regularity conditions, so which just some integrability conditions, fairly weak, you can actually prove that the mutual information of the original channel, continuous time, is equal to the limit of the mutual information of discrete time channel as the step size of the channel goes to 0, but of sampling goes to 0. So if we think about it, this couldn't be more natural. I mean, this extension. So before classical sampling theorem actually says if the bandwidth is limited, you can actually reconstruct exactly based on the time samples. But right now we're saying if we don't have bandwidth limit, we can actually reconstruct the mutual information almost if the sampling is fine enough. So it's very, very natural idea. And so let's look at the proof. And the reason we actually have a relatively weak assumptions, as I said, regularity assumptions are actually just integrability conditions, is we actually use some Jitanov theorem. So if you use Jitanov theorems, you can actually calculate the random Nikodym derivative of y with respect to b as follows. And over here is a conditional version, conditional m. So then you do some kind of marginalization. You can actually have the random Nikodym derivative evaluated at the sampled output. So right now, so they're not continuous. They're actually only the sampled output. But in that case, we can actually say something about convergence. So for instance, by the definition of mutual information, the mutual information of discrete time channel is equal to this, right? But now the two random Nikodym derivatives, they are all martingales, which guarantee the almost sure convergence. And then you apply the usual argument for general Lebesgue dominant convergence theorem. You can actually prove that not only the derivative converge, you can also prove the expected value of log derivative also converge. So this for here we have a conditional version. Then you can actually prove the unconditional version also converge. I mean the expected value of log of derivative. But that goes back to the original definition of the mutual information of continuous time channel, which can be written as this. This combined with that and the convergence you see already in the previous page, I finished the proof. Right, so I finished the proof. Okay, so that's the sampling theorem. So basically saying the fine enough sampling will keep almost all the information. Okay, so what about the approximation theorem? So before I do that, so let me again introduce more notations. So first thing you need to know is the so-called Euler-Maruyama approximation. So let's say we have a continuous time Gaussian channel right now with feedback again. So so instead of doing sampling, so sampling just, as I said, you take snapshot, right? At T0, T1, Tn. But right now we're going to approximate this channel. So instead of just take a snap. Yes.
I have a question. So when you took the limit before, is the sampling each step finer than the previous one?
And for the previous one, it does require this assumption, yes. But for this, it doesn't. I did not state completely the statement. Otherwise, you don't have a martingale convergence theorem.
Martingale property, you can't just sample it finer and finer in any way you want. You have to.
Exactly. You have to be like the sigma algebra where you guys saw larger and larger. Yes, you're right. You're right. I did not state that. Okay, so then the Euler-Maruyama approximation basically says the following. So instead of doing the sampling, take the snapshot, we're going to approximate the original channel. So what we're going to do is to replace this x, the integral of this input, by the corresponding discrete time version. So notice that before we have continuous time pass output, but right now we have discrete time pass output. So that's the reason we actually have x delta, which is different from the integral of x. But then, so after replacing that, then we have this, we can define y tilde. Y tilde is basically just what we obtain after replacing x by x tilde. So, but right now the significance of this approximation is that right now you're looking at a discrete time feedback channel that you typically see in information theory, right? So before, all the previous output has been hidden in here. So rather than so we actually, in a way, we kept the temporal causality. So this is the channel we have known, we have studied, quite a bit, and we have a lot of experience working on this channel.
Can you say how to correct the formula there? There's something with Ti on the left, and I don't know where the Ti is on the right. After your where, your x tilde of Ti, there has to be Ti on the right somewhere.
Oh, sorry, here should be Ti.
And you integrate from Ti minus 1 to Ti or from 0?
Here should be Ti, I think should be Ti, or here's the Ti minus 1.
And the 0 is still the same?
0 should be the same, because it's not
good.
from 0.
Mm-hmm.
Sorry about the typo. Okay, so now we have another discrete time, the approximating the channel. Again, x tilde and y tilde are different from the snapshot, from the sample. But still, we can actually assume some regularity conditions. The regularity conditions actually are pretty ugly. So let me not show you, but but assuming those regularity conditions, we can actually prove that the limit of this the mutual information of discrete time channel will converge to that of the continuous time channel. And obviously, as you may have known already, that the mutual information between the message and the discrete output can be written as the direct mutual information from x tilde into the y tilde. Okay, so let me just quickly mention that when there's no feedback or memory, actually our approximation theorem is exactly the same as the sampling theorem. But when there is a feedback or memories, they actually diverge. Right? So they're different. Okay, so one-line proof, some bounding analysis, which I will now show you. This is very tedious and ugly. and tortured me for several months. So I'm not sure you hate it. I'm sure you will hate it too. But still, I mean, like I said before, if you really want to err on a lot of details, so many little things you have to take care of. So let me not show you the proof. Okay, so now, I want to talk about some applications of extensions. So the point is, as I said before, that the sampling theorem, approximation theorem, actually naturally connects the continuous time and discrete time. And even if we have feedback from memory in the channel, so in this way, so instead of studying continuous time Gaussian channel, we can study discrete time Gaussian channel, which we know how to do. Then we just go through the analysis and take a limit in the end. We can say something about a continuous time channel. So let me show you what kind of application we can have. So the first one is a classical formula, reproved using elementary proof. So I'm sure you all already seen this formula before. So here's the AWGN, and so we have y in the x input and b. But right now we assume x is stationary Gaussian process with the power spectral density. Then you can actually prove the mutual information rate is equal to this formula. Here, Ft again is the power spectral density of the channel input, which is assumed to be Gaussian. I'm sure any digital communication undergrad already seen this formula before, but frankly, I'm not sure how many of them know the rigorous mathematical proof because it's highly involved. So very quickly, let me just mention the proof, the old proof. So the conventional approach actually appeared in 62, 63, then later on was really rigorized by Ihara in 1993. Actually used the spectral analysis of infinite dimensional operator of xt. But that really means we need a lot of heavy machinery from functional analysis with stochastic calculus. I don't think the idea actually extremely difficult. It just means if you want to get there, you need to learn a lot of things to understand the proof. So that's the reason I said that probably not too many undergrad understand the proof. But by connecting the continuous time to discrete time, our sampling theorem can help give an elementary proof of this formula. So which only involves basic calculus and linear algebra. Only the idea is actually pretty simple. So our approximation theorem, our sampling theorem actually says that the continuous time the mutual information is equal to approximately equal to the mutual information of discrete time, right? So, but from here, the basic calculus and linear algebra just take over. So the point is, we can actually just apply the whatever we know about discrete time Gaussian channels to prove this. So, as I said, so right now the undergrad can understand, maybe come up with the proof under proper guidance. Well, the reason I say it under proper guidance is because there's some uniformity issues that kind of baffle me a little bit. That essentially, we actually try to connect discrete time Siegel theorem to continuous time Siegel theorem. We'll have to prepare a sort of version of discrete time Siegel theorem in a way so that we can shrink the time lapse between 10 points so that we can approximate the continuous time. So that's the tricky point of the proof. But again, so everything just basic calculus and linear algebra.
What do you assume on the distribution of m?
We do not assume anything. I mean, they can be arbitrary. It doesn't have to be.
Suppose m is binary, then mutual information.
Oh, sorry. Yeah, we actually assume this. We actually assume x is Gaussian.
So m should have sufficient amount of randomness in it. Say uniform 0, 1.
Right. So that x is Gaussian. Yeah. So that x is Gaussian. But that's actually the distribution m is not important, but this is important. X is a stationary Gaussian process.
No. The Gaussianity does not come from the randomness in M. X does also have it's x of s, m, and omega.
I really should to be more precise. Maybe I should replace to avoid confusion. Maybe I just replace the m by x. I mean, basically, I mean the channel input and channel output has this formula. And so that's one of the applications. I mean, the idea is pretty simple, right? So instead of studying continuous time, so So rather, we can study discrete time, then so do whatever we can do using the knowledge there, so we get some results, then take a limit. Right? So that's the rough idea. Okay, so that's for mutual information. So we can also study the capacity. So let me just either in the point-to-point setting or multi-user setting. So let me just illustrate the approach by revisiting this AWG we had before. But right now, so we have this the continuous time feedback. So we also assume we also assume the average power the power constraints, and here's the power constraints. Then, as already seen before, we're going to apply the Euler-Maruyama approximation. So here's what we obtained for the discrete time, the feedback channel. And by our approximation theorem, so if we take a limit with the mutual information, we have the mutual information of the original channel. Okay, so then you go through the analysis. You already seen it many times in discrete time Gaussian channels. So go through the analysis, you have this upper bound over the mutual information of the discrete time channel. But notice that when the delta n goes to 0, so this is essentially the integral of the squared input. But that will give us the upper bound, PT over K. So that shows the converse part of the capacity formula. But if we notice the proof, actually, if we choose the input x to be independent Gaussian already, so you can the integral sign can be pretty much replaced by the equal sign. Then we can actually prove that non-feedback coding scheme also achieve this P over Q. So that shows you the idea of the y, the capacity formula y is C is equal to P over Q. Okay, so this kind of analysis can be applied to multi-user setting too. So, for instance, you can consider continuous time Gaussian channel, Gaussian MAC channel, multiple access channel. So here's the channel. So we have multiple input x1, x2, xm. Then those two input add up together plus a noise. It will give us yt. So this is a multiple Gaussian multiple access channel. Then going through the same analysis, you can prove that when there's no feedback, the capacity region actually is given by this rectangular area. But notice that the argument I gave is basically heuristic in nature. It doesn't really give you a rigorous proof. The rigorous proof actually takes much more than that. In particular, the rigorous proof actually uses the following lemma. I'm not sure how much you can get out of this lemma, but the point is, this lemma actually trying to say for the continuous time Gaussian multiple access channel, in order to achieve the capacity, you can basically treat other users as noise, right? And then you do not lose any data transmission rate asymptotically. So that's the key lemma in the rigorous proof. It's kind of funny that the same analysis can be applied to Gaussian interference channel. So for instance, if you have this Gaussian interference channel, so we have multiple input, so x1, x2, xm, and we have multiple output y1, y2, ym, and also assuming it's average power constraints, then when there's no feedback, the capacity region is also given by rectangular area. So this is for the Gaussian interference channel. So, but notice that the discrete, of course, I'm sure you already know, the discrete time Gaussian channel was extremely difficult to study. But that doesn't mean the limit is also difficult. Actually, we have the case that the continuous time Gaussian IC is easy to deal with. Then you can actually say something about the Gaussian BCs, broadcast channels. So it turns out when there's no feedback, the Gaussian broadcast channel, the capacity region is actually a triangular area, triangular region, which takes the following form. And the rigorous proof actually uses a so-called continuous time version of the entropy power inequality. I mean, it really depends on how you see it. But entropy power inequality, in a way, can be regarded as a concavity result or a monotonicity result. So this actually the theorem actually depends on the following results, which is continuous time version of entropy power inequality. So let's say we have such a Gaussian channels, then the lemma actually shows that the mutual information of the continuous time Gaussian channel divided by S and R is a monotone decreasing function of S and R. So it's a kind of monotonicity results. Okay, so that's for the multi-user settings for the multiple ISAC channel and for the BC channel, for the interference channel. So for which we always assume there's no feedback. But what about the case that feedback might be involved? And over here we have actually some results. So feedback will not increase the capacity of continuous time physically degraded Gaussian BC. Okay. But however, it may increase the capacity region of continuous time stochastically degraded Gaussian BC. And the way you can see that actually is this very high level explanation. So obviously this just by the look is obvious, right? So if A n is equal to B n, the limit should be equal. If A n bigger than B n, then likely that the limit is bigger than limit of A will be bigger than B n. Or put it differently, for a Gaussian channel, is a BC channel, if the feedback doesn't increase the capacity for the discrete time, then I will not increase the capacity for the continuous time. And if the feedback does increase the capacity for in discrete time, then likely we will have in continuous time that the feedback also increase the capacity. This is essentially they're trying to say that our approximation is connecting the discrete time and continuous time. So one-line proof, it's not exactly one line, but I can make it so using smaller font. So one-line proof is actually for the physically degraded BC, we can use the argument in our Guangyue in 1984 plus our approximation theory. We can actually prove that it is a statement for physically degraded Gaussian BC. And in Ozaro Liang in 1984, where they actually proved that the feedback does increase some stochastically degraded Gaussian BC in discrete time, and plus our approximation theorem, we can prove the statement for stochastically degraded Gaussian BC. Okay. Then for the IC channel, the feedback may increase the capacity region for continuous time Gaussian IC. So this actually will apply the arguments in Su and Cei in 2011, where they show in discrete time in Gaussian IC the capacity region may be increased by the feedback, and plus our approximation theorem, we can have argument for this theorem. Okay, now you pretty much see the pattern, right? So whatever we have this discrete time, we may have in continuous time by our approximation theorem, but that's not the case anymore for MAC channel. Okay. So for the MAC channel, actually feedback will not increase the capacity region for continuous time Gaussian MAC. So this is the example, this is a counterexample, maybe I should say, that feedback, not everything we have in discrete time can be translated to continuous time. So the point is very high-level explanation. So even if A n is bigger than B n, we may not have the limit of A n bigger than B n. So they can be equal. Right? So even more detailed explanation will be, and the reason that in discrete time feedback does increase capacity is essentially because of this. And this is this quantity is strictly less than that. But if you take the limit, which is equivalent to say that let P1, P2 and go to 0, then we take the limit, then the P1 plus P2, and this limit, which will be equal to P1 plus P2 divided by 4, will be exactly equal to P1 divided by, or here's 2, plus P2 over 2. So before feedback does help, right now feedback doesn't help in the limiting case. Okay, so if you want to see the rigorous proof, which is actually just a typical copy of the framework you have seen already so many times in information theories, basically just follow the usual framework of converse part proof, achievability part proof, except everything you see right now. So like Y over here, they are continuous time. So which means you have to deal with some actual technicality issues. So for instance, I mean, if you want to evaluate the mutual information, you probably have to use this formula by Kadota, Zakai Ziv in 1971, so to have this formula to prove that the transmission rate is both of them is less than P, either P1 or P2 divided by 2. So this formula will be instrumental. And so that finishes the converse part. So even if I have, the feedback in the input, so still we have this upper bound for the capacitor region. And the next part will be the quick proof the quick copy of the random coding argument. So still we're going to generate random codes. Right now it's based on the process rather than simple random variables. Some technicality issues, for instance, you really have to define a typical sequence differently than in the discrete time. In discrete time, in entropy rate, they all make sense. But in continuous time, entropy rate, they do not make sense. They're always equal to infinity. So you really have to define the typical sequence using relative entropy, relative sense. So this is some of the technicality issues you have to deal with. Then you pretty much go through the same analysis. Then you see the ergodicity for the continuous time process. That's the continuous time Shannon-Nyquist-Bryman. But again, so the framework actually follows. And the key point actually is this part. I mean, this is the part where I apply the key lemma, basically saying that in order to achieve the capacity, the user can ignore the other users. You just treat them as noise. You do not sacrifice the transmission rate asymptotically. Okay, so with that, I finished all the technical part. But let me just quickly mention some concluding remark. So we have some extensions of Shannon-Nyquist sampling theorem, and that will connect discrete time and continuous time. So something we can do in discrete time can be translated using the sampling theorem or approximation theorem into continuous time. Okay. Then of course we want to generalize our theorem so that it can be applied to more general situation. And that probably depends on whether we can develop some information-theoretic theorems in stochastic calculus. But I mean, regarding the applications of current extensions, in my opinion, it's really nothing shockingly new or genuinely novel. I mean, we're simply not there yet. So we have secured some low-hanging fruits. By translating or by modifying the current proof to from discrete time to continuous time, but it's really nothing shockingly new. In the hindsight, actually, it's pretty natural. We have results like I presented. How deep and how far we can go with these extensions, it remains to be seen. Or should I, to finish my job, so what about continuous time machine learning? To mention the word machine learning. Anyway, so let me just quickly conclude. And I want to thank a lot of people we talked to for this work. And they gave me a lot of suggestions and comments and pointed out the relevant references. And I want to thank you for your attention. Thank you very much.
Time for some questions?
Yes.
So suppose that you are okay with the bandwidth approach,
Mm-hmm.
and then for math, you can probably just assume it is just a discrete time channel with these many degrees of freedom.
Mm-hmm.
And I mean, just assume for a second that is actually time domain as well.
Yes.
Then you can apply the usual bounding technique, and in the wideband regime, when things are spread out over bandwidth, you are kind of slicing your power over the very wideband, and then that heuristic approach will probably show that the feedback doesn't increase the capacity region. So I'm not saying that is a right way of doing it, but wouldn't it give you some intuition about how the solution will look like for interference channel, for example?
I know exactly what you're talking about, but my way of thinking is really, I mean, if you, I mean, the very basic point is the conversion from continuous time to discrete time for Mach, for instance, will destroy the temporal causality. And after the conversion, even for Mach, when you have feedback, so basically your feedback or your previous output will scatter around to basically every, you know, every n, which is a space index. So that's not a typical that's not a typical channel in information theory. And there might be, I mean, I know you're actually, what you said, very natural idea, but if you look at those channels, they're not feedback channel, because your previous output may be in a bigger n. I mean, that's my rough explanation. So that's the way I feel like it's difficult to overcome, to how to preserve the feedback. Because, I mean, again, roughly speaking, the previous feedback, let's say in time 5, may goes into the coefficients in Z10, something like that. So that's the difficulty I have a difficulty to overcome.
More questions? Yes.
Do you think that that your approach would also work for matrix-valued Gaussian channels? Just 4x4 matrix, all the entries are of your form. Neutral information is still well defined.
I would say, if assuming the average Gaussian average power constraints, this approach probably work. Yeah, I would say so. I mean, if it's average power constraints or power constraints, it can work. But I try to go a little bit further, try to go beyond the average power, try to study, try to look at the situation where we have peak power. This is the situation really changed everything. So I cannot do anything there. But my feeling is for average power constraints, this approach should work.
More questions?
A quick one. So if I understand correctly, maybe not, but the theorem where you show the limit with t that goes to infinity
Yes.
of the information over t equal to the integral of the log.
Yeah.
Those ones. Yeah, it looks like the Wiener-Knick theorem of power spectrum with respect to intensity of a signal, right?
Yes. This is a classical formula. You're right.
Exactly.
I really should have. The classical way to put it is, well, here's x. I apologize.
But yeah. So my question is, so in this way, you retrieve the information, the mutual information, while in the standard theorem you retrieve actually the signal. So it looks like you have less. So in the lab, when you take like for example an oscilloscope, the power spectrum, you get something that you can use to extract numbers. This seems a bit more abstract than.
You mean the proof, like
no,
proof here?
I mean the application of this, because usually.
This is the amount of information, not the information itself.
So you cannot retrieve the signal in this. The signal is lost.
It's not lost, but anyway, I should let this
Yeah,
speaker
okay.
No. Basically, so I mean, over here it should be over here, so it should be x, and everything actually is pretty Gaussian. So everything is computable, particularly if you got here. So this should be Gaussian, over here should be Gaussian. They are discrete time Gaussian. Then you can actually compute. This is essentially log 1 plus some determinant. It's just right now the calculus and linear algebra comes in. So assuming you solve the uniformity issue, that baffles me quite a bit, then you can prove the formula just using elementary stuff.
Let's thank the speaker again.
Thank you.